Good afternoon to all of you. Doesn't look like I'm as popular as the last guy. He was really popular. So maybe you may change the mind a little bit. Just a little background on Solarflare if you've not heard of us. We've been in networking solutions since 2001. We deliver network interface controllers, all software that goes on top of that, plus additional software that we provide for Linux environments. We've really been very much an Ethernet company based on accelerating and improving Ethernet connectivity, and we've been very successful in some of the most demanding space in the industry, like high-frequency trading. So almost all the trades you see today run across our network solutions, and I'm going to talk about one of those technologies we're bringing to a broader market that are significantly improving in performance. So my talk is about that today, about the specific technology. And it's not just us doing it, many other companies are trying to get there the same way as we are, and how it impacts NGINX in the various usage models. Before I get into that, I'd like to take a little survey of the people in the audience. How many of you guys deploy NGINX reverse proxy load balancers? Has anybody done them? So 1, 2, 3, 4, quite a few. How many do web services on NGINX? 1. So this is going to be pretty interesting for you guys. For other guys, it may be eye-openers for other applications that may be running on NGINX that require some very interesting performance gains. So let's get going. So we look at the modern data center. We see these various facets from scale-out computing to software-defined everything, flash memory, security. But what today's focus is going to be around what's transitioning in the data center and servers, which is where everything really runs on top of. That's changing significantly the importance of I/O, why I/O matters to even applications and high-level applications that run on top of that, around multi-core systems and virtualization. So we're going to focus in that space for the moment. One of the key things that I look at is I've been in the networking industry from the very early days of network connectivity, even before TCP/IP became popular, in the earlier days of non-standards. The key thing about this is the network architecture that we run today, all our servers on, is about a 30-year-old technology. And its architecture is designed in a specific way to solve the problems in the original day. I want a piece of wire that can connect up to my server, and I want to translate those serial bits and bytes coming in into something that I can present to an application, and an application can use that and then send something out. That's fundamentally where it was. And in the older days, monolithic systems, that means systems that had single CPUs and single cores, or may have 2 CPUs or 4 symmetrical CPUs, that was fairly adequate. But what you've got going on right now is an explosion of the number of cores inside a server. I mean, today we're averaging around 22 cores per server. The next generation platform coming at the end of this year, and then the following year from both Intel and AMD, your core counts are going to go from 22 average to 48 to 128 within 2 years. So now think about that. That's the equivalent of you putting together systems that would have 128 parallel processing capabilities. So your I/O has to match that. If your I/O is inadequate in making sure the messages move from the wire up to your application in a very consistent manner, you're going to suffer from a lot of bottlenecks. So you may buy a 28-core system, but you may only achieve a fraction of those number of cores, even though you don't see your cores busy. You'll see it not being able to achieve the throughput and performance that you expect. So one of the key things of that is the way the design of the old architecture of network interface controllers and the software that ran that was designed in the old manner. What we've been working on for at least 15 years, and it's pretty well founded right now, is changing that design of the network interface to be cognizant that there could be millions of flows, millions of connections coming through to a single pipe on a system that wants to talk to hundreds and hundreds of cores sitting inside the system. If you think about it, if you go more higher than that, and I'm going to get to the software in a minute, if you go higher than that, what you're actually doing is every core today is performant to maybe a couple of threads. In next generation coming out, you're going to go up to 4 fully functional threads per core. That's a significant increase in performance that you're going to get. So the bottleneck that you have on the wire is going to be very apparent. And the pipe speeds, the speeds today are moved from 10 gigabits to 25, moving to 100 very rapidly. We have a project internally that we're working with some of the advanced development that's looking at a terabit pipe. So think about your computer having a terabit wire being connected to it. That's a lot of data. So if your architecture is not ready for that, you're going to find a lot of difficulties. So we have been working very hard at trying to get this problem solved, and we have a solution today that's shipping, and we have another generation coming next year that's shipping that will increase this even further. We can support up to 2,048 concurrent flows going in and out of a 25 or 100 gig pipe, which is a significant increase on where people are today, around 256. So that's one of the bottlenecks that we think is critical. The other bottleneck is really to do with the operating system. Again, if you look at the operating system, even Linux, I was one of the original group working in MIT at an operating system called Multics, which is the predecessor to Unix, and Unix became Linux. This was not designed with multi-core environments in mind. Now, huge amount of progression has been done in the operating systems to address that, but the operating system is the penalty now you pay for whatever you do in the system. So if your application like an NGINX reverse proxy wants to receive a packet or send something or do something, it has to now go through the operating system. Every time you do a call from your application, whether it's a TCP socket or wherever it is, that's going to cause a context switch. That context switch, you can do all the measurements you want. You won't see the overhead associated with that context switch. In real time, that context switch is very, very heavy, because what it's doing is it's saying, okay, this thread that wants to request an application data to be sent is now going to be, all its stack's going to be saved, all its information is going to be saved, and its context is going to be transitioned into the operating system. That transition is an extreme overhead that you pay today, and it's a very, very high penalty. And I'll show you some of the numbers later on that you can see how significant that penalty is for these NGINX class applications. And if you look at it even further, you also, once you get inside the operating systems, now the number of concurrent operations you can do inside the operating system to send and receive things are limited as well, because there's a limited amount of system resources to manage that. It's not infinite. And there is some amount of serialization goes inside the kernel as well, so not everything can be done in parallel. So that creates another bottleneck, and then you copy buffers because you can't have user space stuff in kernel, so you have to copy all the information you want to send into the kernel space. So that transition is what the penalty that I talk about in terms of context switch and buffer copying. I put a little star there to indicate any application you have, whether it's a web server or a database engine or anything, when it does an I/O call, it's going to go through this process. So the problem there is extreme. Now, what we did with our wonderful technology, we created hypervisor, virtualized environments. And what we created is virtual machines that you put the whole operating system inside a virtual machine, and then you put that on top of another operating system called hypervisor. And if you look at it from this context, you now pay double the penalty of the overhead, which is where the significance of this issue exists. So even in a highly virtualized environments, your ability to move data in and out is encumbered in multiple ways. Number one, you're in a virtual machine, so when you do a request, you do a context switch within the virtual machine. And that virtual machine says, oh, I got to send this data, and it causes the system to trap and instigate another context switch down into the hypervisor. Then the hypervisor then starts to move that data out. So this double buffering is really create. So you may not notice it in most applications because they're not very heavily I/O bound. And the reason I ask why, if you're doing load balancers or database caching or some of those applications with NGINX and web services, those applications tend to be I/O bound, are limited by the number of I/Os and requests per seconds that you can generate into the system. So those applications suffer from this much more than a simple application that runs and just does some database actions or does some function, comes alive and goes away. Whereas in a really high performance environment that we're getting to with these very high performance pipes, that issue is really a big problem. So these are the problem statement here. Even when you go to containerized virtualization, actually containerized virtualized environments are a little bit better than hypervisor-based. The reason is because there is no hypervisor layer within containers. It's using the Linux kernel infrastructure to implement the virtualization. So you're only paying the penalty once there, but the penalty's still there. So we think this is one of the problems. So if I just spend a moment on our architecture of our network controller. This is a software show, so I'm not going to talk too much about hardware. Sorry about that, just for a moment. But our chip allows us to, as we said, process packets very rapidly. This is what we've been designing for years for high-frequency trading, electronic trading. This is what we had to do. So we have a network interface controller that can move data in and out of main memory, the fastest in the industry. So I'll show you some charts in a minute on that. So the network controller has its capability, but not only that, we can not only move data very fast, but we can pass packets and look at packets and decide to do things with them. And that's actually interesting when you go to the future, but right now I'm just going to stay away from that. But that's the core of our chip. So we have that network interface controller. So this is where it really is the key, right? With that ability of our network interface controller to manage thousands of concurrent request operations, concurrent queues, we're able to take a piece of software that we've created, which is called Onload, basically taking the TCP/IP stack out of the kernel and putting it as a binary library into your application space. So when you start your application, you load the binary, and it now behaves as though it is your TCP/IP stack for all your operations. And it is POSIX compliant TCP sockets and UDP sockets. So any application today is written to those various APIs. So with that sort of a interface, that means your application can take benefit of Onload even without changing. No modifications at all. In fact, a lot of the work we've done with NGINX, we just took the standard NGINX, loaded it up, installed our solution, configured it, and ran it up, and you were able to get the performance benefits. So the key point here is that the TCP/IP stack is removed out of the kernel and is allowed to communicate directly with the network interface controller, so bypassing all of that overhead. And that gives you, in the early days, we used this for improving the kernel latency. That means how fast we can move the data out of memory onto the wire and back again, which is very important in high-frequency trading, because the faster you can do those transactions, the faster it is. But translating that to the future where we are today, that kernel bypass technology allows us to cut out a lot of the system overhead, the context switching and everything else, and give you an idea of the types of performance you can gain. The top line is a standard packet without an application payload. You can see the blue bits. The blue bits are what it's taken by the operating system as it goes to the kernel. The blue bits and the lines below that show you how we can reduce the overhead associated with the TCP/IP kernel bypass technology called Onload. So we can significantly reduce the amount of time it does take you to move that payload in and out of the system. So the results of this is really where the things go to. So if I now take the same look at like a containerized system, and we apply Onload libraries binary libraries to the Linux installation of Onload, you'll see that now the operating system is cut out and communications go directly into the adapters. So no interference in between you and your data. So if you want to send a piece of data, you just call it, it gets scheduled, and it just goes out. You don't even move out of context of your operating system into the operating system. And the value of this is if you have something like an NGINX application, which is very efficient doing lots of things concurrently and moving things around, this allows you to cut a lot of the overhead associated with the system out. And it's not incompatible, it's fully compatible, it's still POSIX. The reality is, even though the operating system's TCP/IP exists, we mirror all its configuration and all its management. So if you change the kernel operating system, you change the IP address or filters or whatever it is, it's reflected throughout the system. So if you've got a multi-core system with lots and lots of applications, concurrent applications running, they all can virtually see their own private NICs and go at the speed of the wire that allows them to transit. You're always bottlenecked by the wire performance, the actual physical wire, but that means there's nothing in the way. So this is one view. Another view is when you do it to a bare metal system. You can see on a bare metal system, this would be a typical NGINX load balancer configurations that we've used in the past to demonstrate the value proposition that we get. And whether it's web hosting inside a Docker or outside of a Docker or a container, or whether it's bare metal, the performance is a significant improvement. So with that in mind, I'm going to just put this model up very quickly just to get our head in framework of the types of places we affect. So in a typical cloudy data center, you usually have these content delivery networks that sit at the front of your networks, and you have a bunch of load balancers that's balancing the load across your servers. This is a very high-level view of the world, but it just trying to simplify it. Then you have a cluster of web services or cluster of app services with load balancers, load balancing the workload to those environments. On the load balancer area, we can improve the number of queries per second by 4x in any machine. So the number of queries, so let's take that into mind a minute. What does that mean to you as an application writer or a user? You don't have to worry about headroom of your server, and the number of servers that you need goes down. So we did typical benchmarks on a 6-core Dell machine. It ran the equivalent of a 12-core Dell machine in performance and throughput. So that's the significance of cutting that overhead. You lose no reduction in the application capabilities and performance. You see no incompatibilities. All you're doing is cutting overhead that you don't really need to use in these new modern style servers that we have, including our network controller. So this gives you an idea. And when you're running your app servers or web servers, we see 2x performance improvements. So your web server can run twice as much or twice the number of web services in the same machine as you would do normally, because it's not I/O bound anymore. And I know this is not an NGINX important aspect, but if you look at the back end where you have database caching load balancers like Redis and Memcache and SAP HANA for in-memory databases, where we apply Onload technology to those, we see 4x improvement in performance of those. So without further going down there, let's give you some of the proof. So this is a benchmark we did on a 32-core server. The blue line represents queries per second that's generated out of an NGINX reverse proxy on a bare metal server. That's running within the kernel. The yellow line represents running with OnLow technology, which is our kernel bypass. And you can see the linearity of the performance scale. It's significant. We have one of the largest cloud guys in China are about to go live with this solution on their load balancer using NGINX. It's not hoodoo magic or science. It's just basically knowing what a system overhead is and addressing that with a technology that allows us. We think in 2 years, this technology class is going to be available for all network controllers, and the software infrastructure is going to change. But we're leaders, we're leading the space and enabling companies to be able to take advantage of this now. Any questions on this? Here is a Docker-based web hosting using NGINX. The same manner, you know, we increase the number of workers and messages per second. You can see that the bare metal or Docker kernel-based infrastructure sort of comes to around 400,000 messages per second and ramps out. You can see the Onload almost quadruples that message rate without significant impact as we add workers. This is the most important. If you're doing a 10 or 20 server deployment with NGINX and load balancers, maybe that's not a big deal. But when you're doing a 100 server or 1,000 server deployment and you want to put 20 or 30 load balancers in front of that, this is significant because it impacts your CapEx, OpEx, it impacts your headroom. It's an insurance for you to protect your request. The reason this company came to us is in China every November 11th they have a big sale day, the same as our Black Friday types of sales. And what they found is their load balancers ran out of headroom and they lost a lot of transactions. And rather than just quadrupling the number of servers they wanted to put in there for load balancings, they're going to use this technology to give them the insurance and coverage for those transaction rates. Okay. This is a telling story because it also shows you another problem that you have in any system that you run without this sort of a technology. The left-hand side is the kernel mode, and this is a histogram of about 6 gigabits per second running across the top. And you can see the histogram as you add the number of containers in the middle, you can see that histogram changes. And when you get to about 5 containers concurrently running at this rate, you can see the jitter that's happening in the performance. Not every application is getting the throughput it needs. Some are choking, some are being starved. That's why you see the overall reduction of the performance. This is not to say that every application that you have on a system is going to be generating that much amount of traffic, but it shows you when you get to peak loads that the system will behave in a very erratic fashion. With an OnLow technology on the right-hand side, our kernel bypass, you can see the performance goes down slightly, but there is no jitter because the data is not being bottlenecked or penalized by the operating system. It's going directly straight from the user space into the wire itself. I'm not sure how much of an interest this, but in the same way, when you do memory caching using database caching technologies like Memcache and Redis, this example is Redis. It shows you for most of the queries that Redis generates with our technology installed in the caching nodes, we see significant improvement in performance, at least 4x. And this one, this one is Memcache D, the same sort of story. So I'm not going to bore you with this because we've got tons of these performance benchmarks and we regularly write white papers and we update these on a regular basis. The next subject I wanted to touch on very generally, and I'm not going to spend too much time and give you enough time to ask some questions of me, is to talk, if you guys are familiar with NVMe over Fabrics, are you guys familiar with that? Yeah. So NVMe over Fabrics is basically taking flash storage inside a server and making it work very efficiently within the server. That means directly connecting flash to the PCI bus, which means there is no overhead associated inside the server. And this project was initiated to distribute that storage and allow any server in the cluster to access any flash storage connected to those systems. And the trick here was to make it run as fast as possible. And so what I'm going to take you to is another application of our Onload technology of how we were able to do that. So basically what we did, and in fact it's been ratified and will be available upstream, we did an NVMe TCP plugin. So it sits right on top of TCP, doesn't require anything special. This plugin can be loaded onto any Linux. When you load it up, basically any storage can be addressed from any server within the cluster or within the domain that you're connected to. And we took that and we basically had Dell actually run some tests for us that showed that our solution with TCP, which is the green line in the middle here, I'm not going to spend too much time, another better story here. The green line, we were equivalent to most NVMe over TCPs. We're just running NVMe over fabrics, just running on TCP. What the story became very interesting is Intel approached us and said, we have this very high performance new flash called Optane coming out, and we think there is a bottleneck in the operating system. Of course, our light bulbs went off and said, So they have been working on an industry standard called SDBK, which does exactly the same, but for storage devices. So it allows storage devices, like flash memory, to be accessed by the application directly so they don't have to go through the operating system. So basically what they did was, this is a configuration normally you would see in a system where you've got a bunch of applications that would go through the kernel and down to the SSDs. This allowed them to bypass the SSDs through SBDK. So similar picture I showed you earlier on. They bypassed the kernel. They saw a significant improvement in performance. Clearly, storage I/O has the same problem, especially when you get the flash speeds. And if you guys don't understand the difference between a spinning media, HDD, and flash, a flash is around 7 milliseconds, HDDs are around 7 milliseconds, maybe 6.5 milliseconds in the fastest ones in performance, in latency. And the new Optane is about 10 microseconds. So the magnitude improvement in performance and density of SSD is breaking the system as well. So by going to user space, they were able to pull all that performance back into the applications. So your applications can now run faster on this. And so for us, this was an interesting project because we basically said, what if we then took this environment and married it up with our OnLoad technology so that your flash storage not only can be accessed internally within the machine directly, but anywhere on the network can be accessed at the same time without touching the operating system at all. So the results of that was stunning, and I did a keynote speech at Flash Memory Summit that basically showed some of these fundamental things. So the blue line at the bottom is a baseline of what the latency of the SSD devices were. The first gray line is running the SSD inside the operating system using a Linux kernel. Then the next line is moving it from Linux kernel to an SBDK environment, which is bypassing the operating system. So you could see a 35% lower latency. And the next one down is then marrying SBDK and Onload together. You get down to a 54% reduction in latency. So what I'm trying to point out here is storage using the same approach and technology can be accessed anywhere within the network within 2 hops in somewhere in the range of 7.5 microseconds to 10 microseconds. That's almost like having the storage device in your same machine, but it's now distributed. So we think this is a game changer that's coming down the road next year, where NVMe flash devices in price and density is going to go down significantly, and it's going to allow us to really address that market. So kernel bypass technology is not a one-off view. Kernel bypass technology is something that's going to move, and then the term that we're using and starting to deploy to address this is the microkernel architecture. So if you know about microkernel, is move the libraries and capabilities you need within the application space and tie that into a microkernel so every application can have all its libraries in use space and use it. So this is I/O's approach to microkernel architecture. With that, I'm going to sort of stop there and give you time to ask me questions. And any thoughts? Yes, sir.
So are you achieving this by patching NGINX or anything like a virtual network?
So what we do, the way we implement the NGINX, we have a library that you basically load into the system, and you execute a command and say turn it on, and it becomes available for NGINX users. If you have our adapter card in there, it will be instantly available. If for some unknown reason you don't like that, you just call the command, you turn it off, and it goes back to kernel. So it's a very simple implementation. It doesn't take anything. In fact, what we also do is we have a profiler that we're working on that will deliver you the complete configuration and marry it up with the NGINX configuration files. So that we pass the NGINX configuration files, look at our files, make sure the settings, everything's set properly so that you can get the best performance advantage for that configuration. Yes, we do. We intercept the system calls at the socket layer. And, sorry, yeah. For the moment, the initial deployment is we're working with data center infrastructure providers. Mostly are cloud-based today, so that's where we are, yes. But we do look in the future of, and we believe this is true, and I know Patrick is one of our field application engineers, he's into this. We think when the public cloud infrastructures become more and more bare metal-like, this application will be applicable to those environments as well. Yes, sir.
Is it possible to run space networking in a untrusted, non-privileged environment?
Yes, it is.
Does that mean that to directly access the hardware, does that need to be running as root, or
No, you don't need to run it root. And this is the important thing is that we don't give you root access to the hardware. We give you a queue mechanism to queue up requests and receive requests. So it's a very formalized interface. You can't do anything with that. Just you can send packets and send data and receive data, basically.
So, is a queue mechanism going through the kernel, or?
Sorry.
Is that queue mechanism going through the kernel to a software or?
No, it's directly going through our Onload software. So all the queuing, all the management is done within the Onload. Onload has an ability to see the number of instances of Onload that's loaded. It also makes sure that it correctly addresses all of those. So you may have one application per Onload. You could have 5 applications talking to the same Onload in user space. It really depends on how you configure and set it up. It's very, very flexible. And we can, of course, if you're interested, Patrick and I can sort of get you some more information on that. And if you are really interested, it is on GitHub, right? We have an open Onload documentation and source available for people to look at. It's not going to get you these performances, but it's there for people to get familiar with what Onload is about. Any other questions? Okay, I hope that was useful and interesting. Thank you for your time. Appreciate it.